Trig substitution is going to come in handy when we have a sum or difference of a squared variable and a number. And we don't have an extra variable sitting outside that will allow magic to happen to do U substitution. Something like finding the area of a circle or an ellipse, as we see here on the PowerPoint. You end up with the square root of radius squared minus x squared, whatever your radius is. So if you had that extra x, it would be straightforward. But as it stands, it's a little more difficult. So what we do is we take advantage of the Pythagorean identities and do a different kind of substitution that relies on SOHCAHTOA and Pythagorean identities and ends up getting rid of that radical for us and allows us to have something that we can integrate. So we do make some assumptions so that we can have a one-to-one function. If you remember way back when you were learning about inverse trig functions, you had to limit the domain in order to have a function. So we assume some things about our thetas. That's okay, we can do that, we're in control. Let's just kind of review our SOHCAHTOA. So I went ahead and drew a nice little right triangle. If I let x be equal to a sine theta, then sine theta is equal to x over a, opposite over adjacent. So that means opposite over hypotenuse, excuse me. So that means adjacent would be the square root of a squared minus x squared. If tangent is equal to a sine theta, then tangent is equal to x over a. That means x has to be opposite and a has to be adjacent, and hypotenuse is the square root of that sum. If x is equal to a secant of theta, then x over a has to be hypotenuse over adjacent, so opposite is the square root of x squared minus b squared. And that should be a squared. I'll fix it. So let's look at example 1. We notice that we have the square root of a number minus x squared. That means we're going to use sine. So we have the square root of 9 minus x squared, all of that over x squared. This is example 1. I'm going to go ahead and draw my right triangle. Theta lives right here. This is a squared, so 9 is equal to a squared. So a is equal to 3. And since x is equal to 3 sine theta, sine of theta is equal to x over 3. So opposite over hypotenuse. That means our adjacent is equal to hypotenuse squared minus x squared underneath the radical, which is exactly what I see there in my original, there, that's better, in my original integral that I'm trying to solve. So if x is 3 sine theta, then dx is equal to 3 cosine theta. So let's do some substituting. We have the square root of 9 minus x squared, and x squared would be 9 sine squared theta over x squared, so 9 sine squared theta, times dx. Don't leave your dx off. So this would be times 3 cosine theta d theta. That's a common mistake that students make, is forgetting the derivative of the x. So don't forget that it's not just going to be d theta, it's cosine theta d theta, because you've replaced x with sine of theta. Now let's look at what's underneath the radical here. We have the square root of 9 times 1 minus sine squared of theta over 9 sine squared of theta times 3 cosine theta d theta. Alrighty, so far so good. Haven't done anything too complicated. I can replace 1 minus sine squared with cosine squared. And then I still have a 3 cosine of theta d theta. Well, square root of 9 is 3, and square root of cosine squared is cosine, so this is really cosine 3 cosine theta over 9 sine squared theta times 3 cosine theta d theta. Alrighty, well, I can do a little simplifying. I have 3, 3, and 9, so all those numbers just disappear as if by magic. And I have cosine squared of theta over sine squared of theta d theta. Well, I could rewrite that as cotangent squared, but I don't think that's going to help me. So let's replace cosine squared. We have the integral of 1 minus sine squared of theta over sine squared of theta d theta. That way I can divide it into two pieces. I could have rewritten the denominator, but I don't think it would have helped as much. So now I have the integral of 1 over sine squared, which is cosecant squared of theta, minus sine squared over sine squared, which is 1. And now I'm super happy because cosecant happens to have an antiderivative. The antiderivative of cosecant squared, the answer has a co, so it's negative cotangent of theta minus theta plus a constant. Now I have an answer, but my answer has stupid thetas in it instead of x's, but that's okay because I have this little triangle up here and I can figure out exactly what cotangent is because it's adjacent over opposite. So this is negative adjacent is square root of 9 minus x squared over opposite, which is x, minus theta. Well, sine of theta is equal to x over 3, so theta is equal to the inverse sine of x over 3 plus a constant. And we're done. Let's look at the pretty answer. There's my pretty answer. And I have cotangent, and I have inverse sine of x over 3 plus a constant. So anytime your problem has the number squared minus the variable squared, the appropriate substitution is going to be sine of theta. Let's look at another one. Actually, before we go on to a different type, you're going to try one with a sine substitution. So it's really the one we just did flipped upside down. So again, your x is going to be equal to 3 sine of theta. Give it a try. I'll work it out and we'll compare. I warned you in the last section that you should memorize that double angle formula for sine. This is the reason when we have a problem like this and you need it when you bring your x back. But let's go through it. We'd already established it was a sine substitution, so we let x be 3 sine theta. Now, I wrote out all of these steps. You're going to do this a lot. You'll probably want to shortcut it in some way, maybe just write these simplifications right underneath and then go directly to this step where you replace it with 3 cosine theta. Be careful with your constants. It's easy to get lost in those. I ended up with 9 on top and a 3, so 9 times 3 is 27, and then I took the square root of 9 and I got a 3, so I ended up with just 9. I did end up needing my half angle formula, so I had the integral of sine squared because the cosines canceled away. Then I ended up with theta minus sine of 2 theta over 2. I replaced sine of 2 theta with 2 sine theta cosine theta. That 2 canceled with that one. So this is x over 3, which is sine of theta, and then cosine of theta was adjacent over hypotenuse, and I just did 3 times 3 and put 9 in the denominator. Alrighty, let's look at example 3. Anytime you have a plus sign, you're going to use tangent. So let's look at example 3. We have the integral of 1 over x squared square root of x squared plus 4. Now these all happen to have really pretty perfect squares in them. If they didn't have pretty perfect squares in them, you would just have square roots in here. And that's okay. We can make peace with having square roots in our problems. But we're going to let x be equal to 4 is 2 squared, so 2 tangent of theta. Then dx would be equal to 2 secant squared of theta d theta. I always write it down. It helps me to remember it. Now I'm going to draw my right triangle. Theta lives right here. And since x is equal to 2 tangent of theta is equal to x over 2. Opposite over adjacent. So the other side is the square root of x squared plus 2 squared, and you notice that's what we have in our integral. So your missing side is always what you have in your integral. So let's replace everything. We have 1 x squared would be 4 tangent squared of theta. Square root of 4 tangent squared of theta plus 4, and I'm going to stick my dx on top because I didn't leave myself enough room. 2 secant squared of theta d theta. Okay, let's get rid of that 1 so it doesn't look like a 12. There we go. Now, right now I have 2 on top and 4 on the bottom, so I'm going to go ahead and put 1/2 out front. I have secant squared of theta living on top. I have tangent squared of theta living down below, and then this is 4 times tangent squared of theta plus 1, which is the same thing as 4 times secant squared of theta. So it's the square root of 4 times secant squared of theta. So I have 1/2 integral of secant squared of theta over tangent squared of theta, and I'll replace this with 2 secant of theta d theta. Now I end up with, actually, let's put 1/4 out front because I have this 2 living right here. Secant squared on top and secant on the bottom leaves me with just a secant on the bottom. So that's 1 over tangent squared of theta, and secant squared is on top, not on the bottom. Let's write it neatly. Secant of theta over tangent squared of theta d theta. Now, we need to be able to integrate this thing. It doesn't go with any of those simple, let's just replace this with that kind of things. So let's think about what would work. I could replace tangent squared, but then I would have my 2 terms on the bottom. I don't like that option. I'm going to see what happens if I replace secant with 1 over cosine and tangent with sine squared over cosine squared. So this is 1/4 integral. Secant is just 1 over cosine of theta. I have tangent in the denominator, so that means it's really 1 over tangent. So that means cosine squared is on top over sine squared of theta d theta, because this is 1 over sine squared over cosine squared. Okay, let's see if that helps me at all. So I have 1/4. I can cancel one of those cosines with one of those, with, that cosine with one of those, and I end up with just cosine of theta living on top of sine squared of theta d theta. Well, I have sine squared down below, so this is 1/4 the integral of cosine of theta over sine theta times 1 over sine theta d theta. Cosine over sine is cotangent. 1 over sine is cosecant. So I have the integral of cotangent times cosecant, which would be negative 1/4 cosecant of theta plus a constant. Wow, we had to work hard for that. So now I need to know what cosecant is. Well, it's adjacent over opposite, so this would be negative 1/4 of adjacent over opposite plus a constant. And let's see, cosecant. Yeah, that's not cosecant. Darn it. I did cotangent, not cosecant. 1/4 of cosecant. Cosecant is hypotenuse over opposite because it's 1 over sine. So it would be negative 1/4 hypotenuse, which is square root of x squared plus 4 over opposite, which is x, and then plus a constant. Now I have it right. Okay, give practice number 2 a try, then we will come back and compare answers. Okay, so let's look it over. Hopefully we get through it correctly. We already knew that t was going to be equal to 2 tangent of theta, so I went ahead and labeled my little triangle, my SOHCAHTOA triangle. I updated the limits of integration You don't have to. The advantage, I didn't have to bring my t back. If you don't want to update your limits, then you'll need to bring the t back. So I went ahead and updated. So if t is equal to 0, then 0 is equal to 2 times the tangent of theta. So theta is equal to the inverse tangent of 0, which is 0. If 2 is equal to 2 tangent of theta, then 1 is equal to the tangent of theta. And so theta is the inverse tangent of 1, which is pi over 4, where sine is equal to cosine. So this is going from 0 to pi over 4. And you can see, instead of rewriting the entire integral over and over again, I just went ahead and did all my simplifying with my Pythagorean identity right here, and then replaced the square root of 4 secant squared with 2 secant of theta. Then I canceled one of them away. The 2's canceled. I ended up with just the integral of secant. And luckily we learned that in the previous section is the natural log of secant plus tangent. So I just plugged in, and I ended up with a natural log of secant of pi over 4, which is square root of 2, plus secant, tangent of pi over 4 is 1, minus the natural log secant of 0 is 1, tangent of 0 is 0, natural log of 1 is 0. Now, if you hadn't updated your limits of integration, you would have had secant of theta, which would be secant, let me make sure I get it right this time, would be hypotenuse over adjacent, which would be 4 plus t squared over 2. And then tangent would just be t over 2. And you would plug in your 0 and your 2, and you would end up with the same darn thing. Okay, example 5 is a little different, and I also made it generic. It has an a in it instead of a real live number. So let's see what happens when we do example 5. We have the integral of dx living on top of the square root of x squared minus a squared. If the variable comes first, we let x be equal to a secant theta, then dx is equal to a secant theta tangent theta d theta. I'm going to go ahead and draw my triangle. Theta's right here, and secant is hypotenuse over adjacent. So secant of theta is equal to x over a. So hypotenuse over adjacent, that means opposite is x squared minus a squared, which is what is living there in my integral. So this is actually the integral of dx is on top, so a secant theta tangent theta d theta living on top of the square root of x squared, so a squared secant squared theta minus a squared. And again, I'm going to be a little lazy here. I'm going to just write this as a squared times secant squared of theta minus 1. That's still living under that radical. A squared times tangent squared of theta. Still living under the radical. So the square root of a squared is a, the square root of tangent squared is tangent. So I end up with a secant of theta tangent of theta living on top of tangent of theta. Well, how convenient. I just did this a moment ago. This is the integral of a secant of theta. So So it's A, and let's see, did my A's? Yes, my A's canceled actually, because I had a tangent of theta here. So let's get rid of you. I don't need you. Natural log of the absolute value of secant of theta plus tangent of theta plus a constant, which is the natural log. Secant of theta is just x over a. Tangent is opposite over adjacent, so square root of x squared minus a squared over a. And I really don't need those absolute values because we've said that a is a positive thing. So there's my pretty answer. Looks exactly like the one I have here. Your turn. This one's going to use secant. Give it a try. We'll meet back and compare. Okay, let's look this one over. This time our a squared was 16, so a was equal to 4. So t was 4 secant of theta. My opposite was square root of t squared minus 16 because secant is hypotenuse over adjacent. I replace dt with 4 secant theta tangent theta. T squared is 16 secant squared. Square root of t squared minus 16 ends up being 4 times the tangent of theta when we go through all the Pythagorean identity simplification. Tangent cancels with tangent. Secant cancels with one of those secants, and I'm left with 1 over secant. And 1 over cosine is just cosine. The antiderivative of cosine is sine. So I ended up with 1 over 16 times opposite over hypotenuse. Hopefully it went well. Okay, example 6 shows us that we can use this even when it doesn't have a radical in it. So sometimes we have things that we think we could use trig substitution for, and it's not required to have a radical in it in order to use trig substitution. So don't be fooled if it has a sum or difference of a squared variable and a number, then you can try trig substitution. Let's look at example 6. We have a definite integral. We're going from 0 to 3 times the square root of 3 over 2. We have x cubed living on top of 4x squared plus 9 to the 3/2 dx. Now this one is a little different also in that we have 4x squared here. So you could do some u substituting if you wanted to. This is the same thing as 2x in parentheses squared. What I generally do is I say that 2x is equal to square root of minus 3. I have a plus sign, tan theta. And that way I can just avoid having to u substitute and trig substitute in the same problem. So then 2 dx is equal to 3 secant squared theta d theta. So dx is just 3/2 of secant squared theta d theta. And you could go ahead and say that x is equal to 3/2 tan of theta, just simplify things. Now, 2 times 0 is equal to 3 tan theta. So when x is equal to 0, so 2 times 0 over 3 would be 0 is equal to tan of theta. So theta is the arctan of 0, which is a big fat 0. 2 times 3 square root of 3 over 2 is equal to 3 tan theta. So we can cancel that 2 with that 2. We divide both sides by 3. That means that square root of 3 is equal to the tan of theta. Maybe you plug it into your calculator. Maybe you think about your unit circle. Remember that it is sine over cosine. And so that means it's going to have a 3 in the denominator because that's when sine has the longer leg. So theta is equal to pi over 3. So instead of going from 0 to 3 square root of 3 over 2, I'm just going to go from 0 to pi over 3. And remember, you don't have to do that. You could go ahead and draw your triangle. Let's go ahead and draw our triangle. I have theta, and this means that 2x over 3 is equal to tangent of theta, so opposite over adjacent, and then hypotenuse is equal to the square root of 4x squared plus 9. And you could always bring your x back and then just plug in those original numbers. So let's see what we have here. We have 3 halves cubed, so 27 over 8 tangent cubed of theta over 4 times 3 halves squared would be 9 over 4 tangent squared of theta plus 9. And all of that is to the 3 halves power. And don't lose your d theta. So let's simplify some stuff here. 0 to pi over 3. Let's see. I have 27 over 8. I'm not going to try to simplify that yet. Tangent cubed of theta. I have a d theta. Now, down below, inside here, I have 4. I have 9 tangent squared plus 9. So I'm going to factor out the 9. That gives me 9 times 4 is 36. Oh, that 4 is only multiplied by that. There we go. That cancels with that. Got to be careful with those parentheses there. Remember that 4 is only going with x squared, so 4 times x squared, the 4's cancel. So I have 9 times tangent squared plus 1 to the 3 halves, which would be 9 times secant squared of theta to the 3 halves. So 9 times secant squared to the 3 halves. Remember, if you have a power raised to a power, that means you multiply. So that 2 cancels with that 2. So what I really end up with is the integral from 0 to pi over 3, 27 over 8. I still have tangent cubed of theta up top. I have 9 to the 3 halves down below. So that would be the square root of 9 is 3 cubed is 27. And the secant squared to the 3 halves gave me secant cubed of theta d theta. I'm going to need to go to another sheet of paper, so I'm going to pause. Were you yelling at the screen? You should have been yelling at the screen. Yeah, I found my mistake. What did I forget? I forgot that thing that I say students forget all the time. D theta is equal to, or actually dx is equal to, oh, that's why I forgot it, because I didn't write it down like, yeah, I did. It's right here. Dx is right here. I should have had 3/2 secant squared of theta d theta. I should have had 3/2 secant squared of theta d theta. And I should have had 3/2 secant squared of theta d theta. Okay, now let's rewrite this, and I'll come back and I'll write it correctly. So, and I took care of the arithmetic. 27 canceled with 27. I still had 3 on top, and then I had 8 times 2. Gave me 16 down below. Still going from 0 to pi over 3. But when the secant squared canceled with the secant cubed, I was left with just secant down below. So that's looking better already. It's making a glare. I don't like that. So 3 over 16, integral from 0 to pi over 3. I don't see any clever uses of tangent and secant that I can do, so I'm just going to go ahead and write this as sine cubed of theta over cosine cubed of theta. Dividing by secant is dividing by 1 over a cosine, so it's the same thing as invert and multiply. So dividing by secant is the same thing as multiplying by cosine. Zero to pi over 3. That leaves me with sine cubed of theta over cosine squared of theta. I think back to the last unit when I had an odd exponent on sine. I usually brought it over and put it with the dx or the d theta in this case. So I really have sine squared of theta on top of cosine squared of theta times sine of theta d theta. Now I'm going to use my Pythagorean identity. 3 over 16, integral from 0 to pi over 3. 1 minus cosine squared of theta over cosine squared of theta times sine of theta d theta. 3 over 16, 0, pi over 3. This is 1 over cosine squared of theta minus cosine over cosine is 1 sine of theta d theta. So I'm going to continue just like I would have in the last one, where I would let u be equal to cosine of theta, then du is negative sine of theta. So this would be 3 over 16. And let's see, we would have to update limits of integration and divide it into 2 pieces, because I really don't want to use substitution on this piece. Well, I guess I could. Okay, let's go ahead and do that. We'll update our limits of integration. Give myself room. U evaluated at 0 would be 1. U evaluated at pi over 3 would be cosine of pi over 3 is a half. So I still have 3 over 16 integral from 1 to 1/2 of u to the minus 1 power minus to the minus 2 power because it's squared, and then minus du because it's the negative of du. 3 over 16. Add 1 to the exponent, divide by the new exponent. So u to the minus 1 over minus 1 minus u, and that is negative, so I'll put the minus sign out front. That came from here, so evaluated from 1 to 1/2. So let's do negative 3 over 16. I plug 1/2 in first, so I have negative 1 over 1/2 because it goes on the bottom. So negative 2 minus 1/2 minus, and then I plug 1 in, so minus 1, that all goes to 0, and I end up with, I'm out of room, I just have to go to a new sheet of paper, negative 3 over 16, negative 4/2 minus 1/2 is negative 5/2. So it looks like 15 over 32. Let's see if I got through it correctly. Oh, 3 over 32. What did I do wrong? 1 minus u to the minus 2. Okay. Looks like I have everything right. I'll take a minute and figure myself out. Yeah, I found it. Minus 1 is minus 2, and then negative of that would be plus 2. So this would be minus 5/2 plus 2 is negative 1/2. So this gives me positive 3 over 32. Always good when I can check my answers. Okay, here's practice number 5. And then we're going to have one that requires completing the square. I wouldn't expect you to do one like that, but I do want you to see it. So, pause, do practice number 5. We'll come back and compare answers, and I'll be sure that it's right before we compare. Okay, it was kind of familiar, except we had the little monkey wrench thrown in that we had something sitting next to the variable. And remember that 25x squared is just 5x in parentheses squared. I went ahead and drew my triangle. So I said that 5x was equal to 3 sine theta. So x is 3/5 sine of theta. So dx is 3/5 cosine theta. I plugged in 0 to the x and figured out that theta is 0. I plugged in 0.6, and since conveniently 0.6 times 5 is 3, that means that sine is equal to 1, and that's at pi halves, so we're going from 0 to pi halves. X squared, square root of 9 minus 25x squared, dx. I didn't forget my d theta that time, my dx. So then I pulled the 9 times 3 over 25 times 5 out front. I did some simplifying underneath the radical, and I ended up with sine squared, just like we did in one of the practice problems earlier. So I had to use my half angle formula. Didn't have to bring x back because I had already updated my limits of integration. So theta minus sine of 2 theta over 2, and 2 times pi over 2 gives me pi. Sine of pi is 0, so I ended up with just 9 pi over 500. Okay, let's see what happens when we have to complete the square. It just means we're going to have to do some U substitution in there. No way to get around it. So, first thing I'm going to do is just complete the square. Completing the square. You can fast forward through this part. So x squared plus 2x plus 5, x squared plus 2x plus 5. So remember how we complete the square. We take this middle term to half it and square it. So that would be 1. I'm going to put parentheses around here. I'm going to add 1 in here. And I have to subtract it out here, otherwise I have a whole new problem, and that's not what I want. So this is x plus 1 squared plus 4. So what I really have here is the integral of dx living on top of the square root of x plus 1 squared plus 4. So, u equals x plus 1 du is dx. So this is the integral of du living on top of the square root of u squared plus 4. That's a job for a tangent substitution. So u is equal to 2 tan theta. du is 2 secant squared of theta d theta. And this tells me that u over 2 is tangent. So opposite over adjacent, hypotenuse is u squared plus 4. Be all ready to bring my u back, and then I'll bring my x back. So this is the integral of du to secant squared of theta d theta living on top of the square root of u squared, so 4 tangent squared of theta plus 4, which is 4 times tangent squared of theta plus 1, which is 4 times secant squared of theta. So this is the integral of 2 secant squared of theta. Square root of 4 is 2. Square root of secant squared is secant of theta. I can cancel away one of those secants. So this, and I can cancel away the 2. So this is just secant of theta d theta, which is the natural log of the absolute value of secant of theta tangent of theta plus a constant. Sorry about that, went off the screen. So natural log absolute value secant of theta is going to be hypotenuse over adjacent, square root of u squared plus 4 over 2 plus tangent of theta, and tangent of theta is u over 2, which is the natural log of the absolute value of u squared plus 4 is our original thing that we had, x squared plus 2x plus 5 over 2 plus x plus 1 is my u over 2. There you go. You could combine some stuff, but You don't have to. So, sometimes it's not going to be obvious, but if you can complete the square, you can work problems like that. We did a lot today, so take your time, practice lots of them. You can do this.